Hello there. Well, I said I would give a bit of an update on our various Wolfram Science initiatives and do some Q&A, which I'm looking forward to. So let's talk a little bit about where things are with our various science initiatives. The big thing that kind of was the breakout thing that started all of this was our Wolfram Physics project, which we launched in April of 2020. That was the result of basically about 40-ish years of work that I've done, which suddenly kind of came together in the 6 months before it was launched as a tremendous piece of progress in understanding how the physical universe is put together. And I must say, I did not think that the level of understanding that we managed to get at that time about how fundamental physics works and how our universe is set up would be something that I would get to see in my lifetime. But actually, it's turned out to be even more remarkable than that. And with the kind of ideas and methods that have emerged from the physics project, it's been possible to see how a whole lot of other stuff works too, in mathematics, metamathematics, and computation, in lots of other areas, in biology, in perhaps in economics, and lots of other areas. It's kind of a new level, a kind of new paradigm for thinking about science. And it's really exciting. And it's something that's keeping me very busy. And it's something where sort of things are evolving every day, every week, every month. New things are happening. There's a lot to do, both in the areas that we've already kind of pioneered and in areas that are yet to pioneer. For example, in our physics project, there's a huge amount of detailed work that has to be done to fill out the basic concepts that are the framework of the physics project. You know, it's an interesting thing because in a sense, the starting point of our physics project is the realization that, for example, space is not continuous. It's not something where space is not just something where you put things wherever you feel like in space. Space is made of something. Space has a structure. Space is made of some giant hypergraph of atoms of space. And that idea that sort of space is made of something, that the universe is not just a thing where space exists and you put things in it, but that space itself has a structure, and that structure sort of is the fundamental structure of the universe. That idea is, in a sense, a foundational idea of our physics project. And there's an interesting resonance that I've recently been realizing, because I've been recently studying, maybe I'll talk a little bit more about this later. I've recently been studying the second law of thermodynamics, the law of entropy increase, which is something that I actually got interested in 50 years ago. And I kind of started studying it at that time when I was 12 years old or something. I think finally, now I am sort of coming to closure on that project as a result of things that we've learned from our physics project. But one of the things that's happened in studying that project is going back and looking at some of the history of people thinking about thermodynamics, second law of thermodynamics, and so on. And about 150 years ago, people were very confused about whether material substances were made of atoms or were continuous. So something like water, people thought it was a continuous fluid that flowed and there wasn't anything discrete. There were no atoms that it was made of. And that was something until really the end of the 1800s, people thought that it was likely that everything was made of continuous stuff. And there had been people talking about atoms in the 1600s. There had been people talking about atoms in antiquity, but that isn't what's actually going on. And I was kind of charmed to realize that some of the arguments that people gave about why things like water are not made of atoms in the late 1800s are bizarrely similar to the arguments that people might have given today for why things like space are not made of discrete stuff. So, but the thing that was sort of the breakthrough in terms of the atomic theory in the late 1800s and so on, there had been indications from chemistry, from the way that sort of integer numbers of types of atoms would show up in chemical reaction equations and so on. There have been indications about the existence of atoms, but let's actually see an atom. There have been things like Brownian motion. There have been things later on. There were things like the discovery of the electron and so on, which made it sort of plainly clear. There were experiments that were kind of clever experiments that kind of made the atomic theory really clear. And for our physics project, I am sure that there are similar experiments that will show that the structure of space is discrete. We don't know what those experiments are yet. We have some ideas, but that's kind of a different type of question from the question of how you build the actual physics theory, is the question of, well, what is that clever thing that you can notice that is, the pollen grain bouncing around on some water looked at under a microscope? What's the analog of that? That's the clever and unexpected thing that shows you that actually the structure of space is discrete. What is that kind of, in a sense, space-time gravitational microscope or something, which will show you down to the level of atoms of space? We don't know that yet. That's one of the things that we like to figure out. And when it comes to talking about kind of the structure of physics, I think the thing that is probably, for me, the most obvious kind of big trunk of development in the physics project as such is really nailing down the formalism, going from this idea of this hypergraph of atoms of space and the rules by which it's updated, going from that idea to something which we can actually in detail see sort of all the steps to sort of build a kind of mathematics that's based on that. The mathematics that we have right now, a lot of mathematics that's based on kind of calculus, is based on the idea that in the end, at the smallest scale, you can assume that things are like Euclidean space, that things are made of manifolds and so on, where at a sufficiently microscopic level, sort of space is this continuous thing that is kind of the way that Euclid thought it was, with just arbitrarily small points embedded in a continuum. And this question of okay, so how do you build a kind of mathematics that is not with that assumption, which has some fundamentally different notion of what is at the lowest levels of space, and how does that work? That's something that we've done a certain amount of in the physics project so far, but I think the thing we now need to do is to solidify that kind of trunk of mathematical development. It's things like, people learn calculus, they learn, single variable calculus, and then they learn multivariable calculus, and they do two-dimensional calculus, three-dimensional calculus. We need fractional dimensional calculus. We need things like that, where we're generalizing these notions that have existed in some cases for the last few hundred years about sort of how one sets up this kind of mathematical structure. We need to generalize that, and we need to do that in a sufficiently solid way that we can sort of build all of this physics theory on top of it. And there are particular kind of pieces of things to look for. For example, we have some idea of how, we have a good idea at this point of sort of how the overall structure of space-time and phenomena like gravity emerge from this underlying structure of this collection of atoms of space and so on. We understand things about that. We'd like to understand things like how particles, like electrons and so on, how those work. We have a pretty good idea how they work. They're kind of like vortices in a fluid. They're these kind of topologically stable structures that exist on top of this kind of bubbling sort of sea of transformations that get made in this hypergraph that represents the structure of space. They're sort of the robust things, just like a vortex in a fluid is sort of a robust piece of motion that sits on top of all of that detailed, microscopic, somewhat random motion of molecules that's happening at the lowest levels in the fluid. We need to understand, how do we find particles like electrons and quarks and so on? And my guess is that when we start finding those things, we start understanding how to get those things out of these models, that will be a very strong argument for kind of the necessity of the underlying structure that exists in our physics project. And quite possibly there'll be sort of relations that we find about those particles and so on, about the symmetry groups and the gauge groups and so on associated with them, that are kind of, that perhaps play a little bit the same role for us that things like the kind of chemical version of atomic theory played in the development of atomic theory 150 years ago, where one could sort of see these remarkable mathematical features that emerge that would be explained if there was this underlying kind of structure, and that's kind of an argument for that structure. Now, I should say another thing that I consider to be an important frontier for us. We have some sort of early indications of being able to use our models of the discrete structure of space-time as a practical way to do computations of gravitation theory kinds of things and black hole mergers and all those kinds of things. We want to really strengthen that and really be able to use our models as a practical way to do kind of actual calculations in general relativity, except they're really calculations in our models that happen to be the same as the calculations you would do in general relativity if you first sort of took the limit of going to the sort of continuum representation of general relativity. So another big area for us in the physics project is quantum mechanics, which is kind of a necessary feature of physics in the models that we have, because we have this set of underlying rules that are being applied to this hypergraph. And the whole point is that these rules get to be applied in a whole collection of different ways, producing this whole sort of collection of different threads of history that can exist in the universe. So the idea is, and this is sort of a core idea of quantum mechanics, there isn't just one history for the universe. There's this kind of whole collection of possible histories for the universe. One of the things that was something that we noticed early in the physics project is the importance of the fact that there's both branching of paths of history and merging of paths of history. That creates this multi-way graph of sort of that is the network of paths of history. And then the important thing that we realized is this notion of branchial space, the space of kind of quantum branches, that when you slice across this multi-way graph at a particular time, you have all these different possible threads of history, and they have these relations to each other because different threads of history might have common ancestors soon beforehand, and that relates those threads of history. And so you get to kind of lay out the different threads of history. You get to lay out the possible things that could have happened in the universe in this kind of space, where instead of in ordinary space, one will be sort of laying things out according to sort of some notion of physical space. Here one's laying things out in a notion of branchial space. Which branch of history is close to which other branch of history? And then the thing we've realized is that the sort of the story of quantum mechanics is a story of how we, as observers of this, perceive this kind of complicated branching, merging multi-way graph. But the important thing is that we are embedded within this multi-way graph ourselves. Our minds, our brains are performing the same kind of branching, merging kind of thing that's happening to the rest of the universe because we are part of the universe. And so in a sense, the story of quantum mechanics becomes this kind of hard to understand story of how does a branching brain perceive a branching universe? And we're gradually homing in on exactly how that works and what that all means. We can see already in the actual formalism of quantum mechanics that we can very nicely reproduce kind of the sort of quantum information, quantum computing kinds of things. Very directly, we can take sort of quantum circuits, compile them into multi-way graphs, do all kinds of interesting optimizations there, get results back as quantum circuits and so on. We can see this sort of correspondence between the traditional formulation of quantum mechanics and the formulation that we have of quantum mechanics in terms of multi-way graphs. We have sort of an underlying machine code of quantum mechanics from which existing quantum mechanics emerges. One of the features of our version of quantum mechanics is in ordinary quantum mechanics, the measurement, the act of measuring things is just sort of an atomic act. It's something that it's just like, and then you measure things. In our sort of model of quantum mechanics, you're going underneath that. You're being able to see the structure of what's going on inside there. And you realize that to have a good idea of what's going on inside there, you need a model for the observer, a model for us. There have to be certain features of the observer that you capture in order to be able to say just what kinds of measurements can get made or do get made. And so just to give a sort of sketch of what that's like, one of the things to realize is that in a sense, well, let's zoom out a little bit about sort of the bigger picture of what we've realized about kind of how physics arises the way it arises. In sort of at the lowest level, we've got all these rules. We can think about them as computational rules. We're running these rules. One of the things that I discovered in the 1980s is this phenomenon I call computational irreducibility. The fact that for a very large class of rules, whenever the behavior you get from the rules is not obviously simple, it will be computationally irreducible in the sense that this kind of computational process goes on and there's no way to shortcut it. You can find out the answer for the computation by just following all the steps in the computation, but you can't expect to kind of jump ahead and see what happens without actually doing the computation. And that's kind of why so much in the universe looks so complex to us, because we can't, with our minds, we can't sort of jump ahead of the systems themselves and just say, oh, that's really simple in what it's doing. We're kind of stuck at the same level of the system itself, going through this sort of computationally irreducible process. So it's sort of an inevitable thing that down at the lowest levels of the operation of the universe, it's full of computational irreducibility. By the way, there's a much higher level of that, which is when you're looking at things like thermodynamics and you're looking at the motion of molecules in a gas or something like this. There too, there is this kind of seemingly random motion, which is actually deterministic. There are definite things that happen when these molecules collide, but the overall effect is this computationally irreducible process, which looks to us complex because it involves this irreducible amount of computation. Now, the thing that's important about studying things like gases is you might say, well, there are all these molecules bouncing around and it's all completely random and we can conclude nothing about how gases work. But in fact, there are certain observations that we make about gases where we can make conclusions. We can say, let's just look at the overall pressure of the gas. Let's look at the overall temperature of the gas. And then we can conclude the gas laws, PV equals RT or whatever. Or we can say, let's look at the large scale velocities in the gas, and then we can conclude things about fluid dynamics. So even though at the lowest level, there's all this sort of complexity, all of this computational irreducibility, all of this unpredictability, nevertheless, there are these large scale emergent laws that are very predictable to us and are fairly simple to make predictions from. So why do we perceive those laws? Well, the main point is because the things that we care about the gas are the things that we as observers can readily observe. So we're pretty big compared to the molecules in a gas. So we tend to aggregate together all of those detailed motions and just say, oh, all we care about is the overall pressure or the average velocity or something like this. So it's that fact that we're big compared to the atoms of the gas, the molecules in the gas or whatever, and we are also looking at these things which are aggregate quantities, these things which are computationally very reduced. And in a sense, the reason we do that is because we are computationally bounded observers. We only can sort of hold a limited amount of stuff in our minds. Our senses can take in data at a certain rate. We couldn't take in the data on all of those molecules bouncing around. So what we're doing is we're looking at sort of a slice of everything that happens. And that slice is the slice where there is computational reducibility. So underneath, there's this whole computationally irreducible process, but the particular things that we as computationally bounded observers choose to sample are things where there is computational reducibility and where we can come up with kind of simple reducible laws to describe what's going on. Well, the thing we realized is exactly the same thing is happening in the case of space-time. Down at the level of atoms of space, it's full of computational irreducibility. There's little that one could say in detail about what's going to happen, but we are taking a slice. Our senses are taking a sort of slice of what's happening in the universe, and that slice, we're aggregating lots of all these details about what's happening in the atoms of space. We are pretty big observers going across, our senses are sampling, 10 to the 100 atoms of space at a time and so on. And so we're concluding these things which are kind of like the gas laws. They're things which are sort of large scale conclusions. So it turns out that in order to go from that underlying computational irreducibility to the stuff that we observe in the laws of physics, we will observe those laws of physics so long as we as observers have certain characteristics. One crucial characteristic is that we are computationally bounded. So there's computational irreducibility underneath, but we are computationally bounded observers. Another thing that turns out to be crucial in studying fundamental physics is that we believe we are persistent in time. So time in these models is this sort of irreducible computational process of the computation of subsequent states of the universe from previous ones. That is what time is in our models. So in a sense, time achieves something. It achieves irreducible computation. The passage of time is the doing of irreducible computation. So there is something that actually is achieved, is changed in the course of time. Well, one of the things that's far from obvious is that we as observers of what's going on are persistent in time, because we are, after all, made of these same atoms of space that everything else is made from. And at every moment, atoms of space are being destroyed, new ones are being created. So the fact that we think that we are persistent in time is a very non-trivial fact. And the fact that we have this belief in persistence in time is what turns out to drive the structure of the laws of physics as we know them. So in a sense, what happens, it's kind of like what happens in thermodynamics, that you can have all these molecules bouncing around, but it doesn't really matter what the details of those molecules are. When you're looking at these computationally reducible slices and you're trying to extract things like the gas laws work for all kinds of different gases, even though their molecules are quite different, because that computationally reducible slice is the same. And so it is with space-time, that once you have observers who are computationally bounded and believe they are persistent in time, it necessarily drives the emergence of general relativity, the emergence of theory of gravity, of special relativity, of all the various features of sort of the structure of space-time that we currently know from physics. So in a sense, that's a feature of us as observers. If we were quite different kinds of observers, we would think space-time worked differently. Just like if we were observers who are quite different in the way that we interact with gases, we would not believe that gases satisfied the gas laws and things like that. We will be discussing, oh, don't you know that there's this complicated causal relationship between these microscopic pieces of what these gas molecules do and those gas molecules do, and that's the important thing about gases, not, oh, there's this relationship between overall pressure and this and that. And it's the same thing that has consequences in the case of space-time. So for example, you can ask a question like, is it possible to go faster than light in our universe? Well, that becomes a question about sort of how you can sort of pick your way through things happening down at the level of atoms of space. Because kind of like in a gas, for example, there are molecules bouncing around, they go, you know, a millionth of a meter or something, and typically before they hit another gas molecule. And if you are trying to ride from one side of the room, you know, the gas molecules themselves might be going at the speed of sound, roughly, and you're trying to ride from one side of a room to another on a gas molecule, if you could pick the exact right molecule at every collision, you could go at pretty much the speed of sound. But to us as observers, we can't do that because we're stuck dealing with things at a much more aggregated level. And so it's a similar kind of thing with the question of whether you can go faster than light in space-time. It's the same kind of thing. And perhaps when you say, can we go faster than light? The answer is maybe no, because we, as observers like us, are great big things with all of our features of computational boundedness and persistence in time and so on. We can't stuff ourselves through those microscopic details, which are sort of threads that can go in effect faster than light. If we were prepared to sort of atomize ourselves down to that level, we're no longer us. And so it's sort of a different question. But in any case, I was talking about a little bit about also quantum mechanics here. You know, one of the things that we can now really understand is that sort of quantum mechanics is the story of all these different threads of history that are all entangled. And we take, when we sample the world at a particular time, we're taking this slice in branchial space, and we can talk about motion in branchial space, analogous to motion in physical space. And it turns out that just as there's sort of a force of gravity that deflects objects in physical space, so energy, which is the source of gravity, energy, momentum, mass is the source of gravity in physical space. So those same attributes are a source of a thing that curves trajectories in branchial space. And the curving of trajectories in branchial space turns out to be the path integral of quantum mechanics. So in other words, one of the great things that we realized a couple of years ago now is that our models of physics imply that general relativity, the theory of gravity and so on, is the same theory as the theory of quantum mechanics, but played out in physical space as opposed to branchial space. But one of the things we realize is, okay, in quantum mechanics, we've got all these sort of threads of history. And when we think about quantum mechanics for doing computations, we can think about all these threads of history being able to do different parts of a computation in parallel. But then if you as an observer want to know, well, what actually happened? You've got to somehow knit these threads together to figure out a definite conclusion about, well, what was the answer to that computation? And in our models, we get to start seeing the insides of that knitting process. And we get to start seeing, can you actually get mileage out of using all this parallelism where you've got all these different threads of history happening? Can you get mileage out of using that parallelism, given that you have to, at the end, kind of knit those threads together to be able to come up with a conclusion that's relevant for us as computationally bounded observers of what's going on? Now, one of the things that sort of we've been realizing, and there's more to figure out here, there are many analogies between what happens in space-time, what happens in branchial space, our extent in space-time, our extent in branchial space, how big are we in branchial space, what does that mean for quantum mechanics, the fact that we are comparatively, the fact that we observe quantum mechanics, we observe these features that are not, that are sort of special to the fact that there are these different paths of history and so on, is a realization that we can actually see down to the level of some of this branching structure in branchial space. But exactly how that works and how we can sort of amplify the effects of the structure of branchial space is something that I consider to be an important challenge right now. One of the things that we do know in our models is that just as there's a maximum speed of light, that's the maximum speed at which things can propagate information, on at least on a large scale in physical space, so there's a maximum entanglement speed that is the same kind of bound in branchial space. And I have this sneaking suspicion that there is a way to observe the maximum entanglement speed in some quantum many-body systems, maybe things related to almost quantum chemistry kinds of things, that there's a way to observe that maximum entanglement speed. There may also be a way to observe it in critical black holes and things like this, but it's a lot easier to do a chemistry experiment than it is to do an experiment with black holes, potentially. So, there are possibilities there. Those we don't really know how those will work out. It's also important to kind of get more intuition about kind of what is going on in branchial space. We have a pretty good intuitive sense of how things work in physical space. In branchial space, we don't really know, what are black holes like in branchial space? What are things like sort of crystalline structure and so on in branchial space? What kind of thing is that like? We're starting to get some indications of that, but that I consider to be an important frontier. Now, another thing is that because we're the sort of merger of thinking about multi-way graphs of these multiple paths of history, and within those paths of history, each sort of state in those paths of history represents a state of the whole universe. There's kind of a different way to think about that, where you're kind of going sort of space first, and you're making this what I call multi-space, where you have space, but different parts of space have this sort of stack of multi-way possibilities at those different places in space. And sort of seeing this interplay between sort of pure multi-way systems that are relevant for quantum mechanics of small numbers of objects and so on, together with this kind of multi-space idea. This multi-space idea kind of feels more like quantum field theory, the theory of kind of sort of this extended set of excitations in quantum mechanics that is our current theory of sort of particle physics and so on. And so one of the things that I think is going to happen is that with our models, we have sort of a machine code that goes underneath quantum field theory, and in fact, underneath quantum gravity as well, because it is this thing that kind of merges the gravity side of things and the quantum side of things. But even underneath quantum field theory, we start to have a way to make sort of a discrete underlying model for quantum field theory, which can then be aggregated up to do actual computations in quantum field theory. And I think that's something that is pretty realistic to do on a comparatively short time scale. It doesn't require, at a technical level, things like lattice gauge theories have tried to do things like this, but they require tricks about rotating to Euclidean time and Euclidean space and so on that I don't think are needed at all in our kind of models. I should mention that sort of the fact that it's the same kind of stuff that's making space-time as is making quantum mechanics, it kind of gives you this way of kind of having a merged theory that is sort of a quantum gravity theory. And it's been known for a few decades that there are these correspondences, holographic principles and things, correspondences between what happens in space-time and what happens in quantum field theory. I think that is basically a realization of the correspondence between what's happening in our models in the sort of full multi-way causal graph that is a combination of spatial degrees of freedom and branchial degrees of freedom. That's the fact that there is one such graph and different projections of it correspond to the space-time part of things and the quantum part of things. That's kind of the origin of those principles that people have seen with other approaches to mathematical physics. I should say also in terms of the physics project, that another big thing is the sort of plugging together of the things we're doing with other approaches to mathematical physics, and there's been progressive progress on that, whether it's spin networks or causal sets, or to some extent string theory, seeing how those kinds of models are various kinds of limits of our models, how we sort of can provide this sort of low-level framework machine code, which has as its limits these various other approaches to mathematical physics. So in any case, that's a very brief summary of some things going on in our physics project, but let me go beyond the physics project, because one of the things about the physics project is sort of, for me, one of the big philosophical mysteries of the physics project was, let's say we actually find a fundamental theory of physics. We got this rule and we run the rule and we say, run this rule and you'll get our whole universe. Then the thing that I was sort of imagining for years is the bizarre mystery of that moment. Because it's like, why did we get this rule? Why wasn't it another rule? Why wasn't it one of the infinite number of possible rules? Why this particular one? And what I realized a few years ago now, is that actually the way to think about it is this: just like in the origin of quantum mechanics, we're talking about applying a rule in all possible ways. So we get all these different branches of history. Well, why not apply all possible rules in all possible ways? What do you get then? Well, the thing you get then is this thing that we call the ruliad. The ruliad is the entangled limit of all possible computations. You can construct it in many different ways. The resulting object will always be the same, but you can kind of describe it, you can coordinatize it in different ways. You can talk about it in terms of Turing machines. You can say, think about all possible Turing machines with all possible initial conditions running in all possible ways for an infinite time. That's one way to generate the ruliad. But the ruliad is this story of sort of the entangled limit of all possible physicses, all possible rules for the universe, all running together. And in a sense, the key idea here is this idea of multi-computation. We have this idea of computation. We have the idea that you have a state of a system, you apply a rule, you get another state of a system, you get this kind of thread of time, and that thread of time is an irreducible thread, and that's the consequence of computational irreducibility, that it's kind of a thread that really means something. You can't jump ahead in that thread, you have to follow the whole thread, but it's just one thread. But now we've got the ruliad and we've got multi-computation, and here we're imagining all these different possible threads. But the thing that's really important is this isn't just a big bundle of independent threads. These threads are continually merging. They're branching, they're merging. Why are they merging? They're merging because, for example, let's say you're dealing with Turing machines. Two different Turing machines can end up evolving to the same state. And so there's, at that point, it's just, well, there's only one state there. We've got these two threads of history, but they merge to one state. Now, one of the things that sort of been realizing particularly very recently is the following thing. Maybe in some sort of outside of everything view, there is no merging. It's just a giant tree. And every possible update is happening, and there's this huge tree of all possibilities of what can happen. But we are observers embedded within that huge branching thing. We're branching too. As soon as we have the belief that we have a coherent view of what's going on, as soon as we imagine that we are, for example, persistent in time and have a coherent view of the world, we have to conflate many of those branches. Those branches are all within us as they are within the universe. But in a sense, that final equivalence of states, for example, in some sense, in some sort of outside the universe view of things, there is no merging of states. All of that merging is a consequence of the fact that we are observers embedded within the system, made of the same stuff that that system is made of, and we have, by our very belief that we are coherent, we are necessarily imagining that those states are merged, and for our description of the world, those states should be considered merged. So, in other words, what we're seeing here is the ruliad is this thing that kind of starts off with this branching in all possible ways. Then we say, we are going to sample the ruliad. Our experience of everything is based on sampling the ruliad from within the ruliad. And as we start to sample the ruliad, and as we start to imagine ourselves as observers like us, who are computationally bounded, believe we're persistent in time, and so on, that forces certain things to be true about the way that we sample the ruliad. And so one of the things we realize is that sampling the ruliad through time, with this persistence in time idea, that ends up necessarily giving us certain features of the laws of physics. It gives us the core laws of physics. That as soon as we make the assumption that we are observers like that, sampling the ruliad itself is this, somewhat ironically, truly unruly place, full of computational irreducibility, worse than just ordinary computational irreducibility, where a single thread of computation, we can't jump ahead. There's also multi-computational irreducibility, where even looking across multiple threads, you can't tell what's going on. You can't reduce that. You can't. So there's this very complicated underlying structure, but we, as a certain kind of observer of the ruliad, are sampling it in such a way, just like the gas laws and thermodynamics and so on, we're taking a reducible slice through all of this, a slice that we can actually make predictions about and understand. And that's our laws of nature. It is not self-evident. In some sense, nature underneath doesn't have laws. Nature is following all possible laws. But what's happening is that by the nature of us as observers, we are sort of imputing to nature certain kinds of regularities. That's what any observer like us, with those basic characteristics of being observers that are like us, will necessarily conclude these things about the structure of physics. And it's kind of exciting that, in a sense, there's so little that you have to assume in order to get kind of these underlying laws of physics, that they are derivable. It is very non-trivial that these laws of physics are derivable. I mean, people thought, it's an interesting feature of the history of physics, the three great theories of 20th century physics, general relativity, quantum mechanics, and statistical mechanics, thermodynamics, those are the three great theories of 20th century physics. People believed that thermodynamics, things like the second law, are in some sense derivable, that by just knowing the mathematics of molecules bouncing around, it will be possible to derive the second law. Actually, it turns out that the second law, its derivation effectively requires observers like us. It requires computationally bounded observers and so on, something I've been recently trying to work through more of the details of. I had figured out much of this in the 1990s, but and even 1980s, actually, but to sort of trying to tie it up now. But in any case, the thing that one realizes is people thought that for 100 years or more, that the second law of thermodynamics might be derivable. They never thought general relativity would be derivable. They never thought quantum mechanics would be derivable. They had thought that those were just ab initio theories of the world that were not derivable from anything else. Turns out all three of those theories are derivable from the ruliad and from the characteristics of us as observers of the ruliad. So I think that's kind of an exciting thing, that that one could sort of imagine that that just by the sort of the necessary structure of the ruliad, together with our characteristics as observers, we can derive the core laws of physics. And they have to be that way for observers like us. Were there to be observers very different from us, very distant from us in rulial space with very different views of the universe, so to speak, then it could be the case that the laws of physics that alien observer imputes to the universe are completely different. Of course, there is then the challenge of us communicating with that kind of alien observer to even be able to compare notes about what is this thing you're talking about the universe. I might say, by the way, that in terms of sort of challenges and interesting features of what's going on, this whole idea of rulial space, the idea that there is the ruliad that represents all possible computations. There's this kind of rulial space where you could imagine, in a sense, different ways to do computation to get to a particular place. We kind of know from the idea of universal computation, and more so from my principle of computational equivalence, that in the end, all these different kinds of coordinatizations of computation will ultimately be equivalent. But there's this question about sort of how you sample this ruliad, how you sample the space of possible computations, and different samplings are sort of different views of the world, and those different views of the world correspond to sort of the way that different minds are interpreting the universe, in a sense. And even within, between human minds, we can think of ourselves, different people might be in physically different places, but they also are in different places in rulial space. Their minds are constructed differently. They have a different way of taking their sort of sensory data about the world and deciding what that means, so to speak. and imputing rules about the universe and so on. And so this idea of rulial space and the kind of the placing of minds in rulial space, I think is a good way of organizing one's thinking about things. You know, we think about, well, there's humans and they're, you know, at different distances in rulial space with different alignments of understanding and so on. You can imagine some artificial, you know, some neural net or something where it has some position in rulial space where it has some way of interpreting things, and you can imagine different neural nets that are sort of placed in different places in rulial space, and maybe that's something one could really make a detailed analysis of because one really can see inside those networks. But then, you know, then we get to, you know, the cats and dogs and things, and they're somewhere in rulial space, and we can kind of partly communicate and understand them. You know, the tail wagging means something that we recognize and so on, but other aspects of what's going on in those minds are pretty far away in rulial space from us. As we go even further away, one of the features of my principle of computational equivalence is that in a sense, there's sophisticated computation going on throughout the universe. You know, the weather really does have a mind of its own and so on, but that mind is far away in rulial space. And it's not something where we can readily kind of, sort of go that distance in rulial space. When we think about SETI and sort of the extraterrestrial intelligence question, there's a question of sort of how far away are the intelligences in physical space. There's also a question, how far away are they in rulial space? And if they're far enough away in rulial space, it's kind of like, it's not really something where we're going to be able to have any alignment of understanding with those intelligences. And it's my guess that the distance in rulial space is pretty large, and it's really quite difficult to sort of impute our kind of intelligence, so to speak. But one of the things I recent realization is sort of an interesting feature of this sort of the correspondence between physics and these other kinds of areas is the following thing. In physics, in physics, motion, it's not obvious that pure motion would be possible. In other words, we're here, we move to somewhere else in space. As we move, we are having to recreate ourselves out of different atoms of space. The fact that we can still be the same us when we walk, you know, a foot ahead or something is not obvious. And in fact, if we were in a part of space that was close to some space-time singularity, we would have a hard time sort of saying we're the same us as we move through that space-time singularity and so on. But the fact is, most of the time, space is kind of uniform, homogeneous enough that we can sort of say there is a notion of pure motion. It is possible to take a thing and sort of have it move without change, or at least without change that an observer like us notices. There is change. It's made of different atoms of space. But to an observer like us, with our sort of computationally reduced view of things, we don't distinguish the atoms of space, the new atoms of space from the old atoms of space. They look like the same. So it just looks like the thing moved. And we can say it just moved rather than it was recreated in a different place. So there's a question. So what it means, for example, a particle like an electron, its big deal is that it gets to be a thing that moves without change. It has pure motion. And maybe the electron, as it moves, it's made of different atoms of space underneath. And it's a very different electron, really, when it's moved to a different place. But from the point of view of us as observers, it seems like it's the same electron. You know, I think there's a very close correspondence between things like black holes and things like electrons. One feature of black holes is that from outside the black hole, you don't get to see anything about what's going on inside. It always just looks like this sort of perfect thing that has only certain attributes that you can tell that don't tell you anything about that, you know, crushed star and the civilization that lived on the planet around the crushed star that was inside the black hole. You don't get to notice any of that from outside the event horizon of the black hole. Well, I wouldn't be surprised if the same thing is true of electrons. To us, all electrons just look the same. All the different electrons in the world are distinguished only by their momentum and energy and spin direction and things like that. There's only a small number of features, but it could very well be that inside every electron, there's a whole world unto itself that is, you know, made of lots of atoms of space and has all kinds of things going on, but all the electrons look the same from the outside. But in any case, the main point here is that electrons, particles, have this feature that they are sort of subjects of pure motion. They can move without change as far as the observer is concerned. So an interesting question, which I don't think I know the answer to yet, is what's the analogous thing in branchial space? What are the particles of branchial space? Not quite sure we know that yet. Then we can ask, what are the particles of rulial space? What are those things that propagate without change in rulial space? And what I think is true is something deeply abstract, that the things that propagate without change in rulial space are concepts. Things like, imagine that we have two minds, and those minds that are at different places in rulial space are trying to communicate. What are they going to exchange with each other? The detailed configuration of those minds, the detailed kind of atoms of existence in those minds will be completely different. They're not, and there won't be a correspondence between them. But there is something that is robust that can be exchanged. That something that can be exchanged is some kind of robust notion of a concept. And that thing, I think, is kind of the analog of a particle in rulial space. So it's kind of interesting to see these correspondences between sort of thinking about physical things and thinking about these things that are kind of generalizations of physics in the ruliad. In a sense, physics is one particular sampling of the ruliad. The physical observer is an observer that's very time-oriented. The physical observer thinks about sort of progression through time of experience. That's the typical way in which a physical observer samples the ruliad. A physical observer is this kind of thick bundle of threads in the ruliad that are sort of going through time in the ruliad and aggregating together lots of different raw underlying computations going on in the ruliad. Sort of interesting to see in traditional computation, computer science, what is often thinking about a single thread in the ruliad, a single computation that's going through there. We, as observers of physical world, are actually much thicker than that. We are sampling big swaths of kind of the ruliad that are not just the individual thread of a single computation specified by a single program. So that's I think, sort of a little bit the analogy between us as physical observers and the computational observer of your average piece of Wolfram language code or something like this. Well, so another question would be, so this is kind of the ruliad as this sort of necessary thing that is constructed out of all possible computations. There's only one of it, because it's all possible computations. You could describe those computations in different ways, you know, Turing machines, register machines, cellular automata, any kind of model of computation you want, hypergraph rewriting, whatever it is. In the end, they're all equivalent and they're all the same ruliad. Now, of course, you could go outside the ruliad. There is a hyper-ruliad. There's a whole hierarchy of hyper-ruliads. And a hyper-ruliad is something you can get to by doing something that is beyond what the rules of computation allow one to do. So, you know, Turing machines can compute certain kinds of things, but if you ask a question like, will this Turing machine ever halt even after an infinite time? That's not something in general that a Turing machine can answer. That's because of computational irreducibility. There's this question of what will happen after an infinite time. There's no way to reduce that infinite question to something finite. But you can imagine, just as a matter of imagination, having an oracle for a Turing machine which just says, okay, I know the answer is X, Y, Z. So the hyper-ruliad is a ruliad in which the computations that are going on involve those jumps, those oracle lookups that go beyond the computations that could be done by any computational system that we think might exist in our universe, like Turing machines and things like this. So the hyper-ruliad is a conceptual object. The hierarchy of all possible hyper-ruliads is a conceptual object that we can imagine, we can talk about, but one of the single sort of contingent fact, I think, about our world is that we live in the ruliad and not in the hyper-ruliad. In other words, that we can ask ourselves, you know, if we imagine our place in the universe, we happen to live in this particular galaxy at this particular time in history. And that's not something that we have a theory for why we do that. It is merely that is a fact that we do that. And so similarly, I think it's just a fact that we live in the ruliad and not in a hyper-ruliad. Now, in fact, there's a whole hierarchy here, because from within the ruliad, we cannot communicate with the hyper-ruliad. The hyper-ruliad, and to the hyper-ruliad, the ruliad looks like essentially a black hole. And even within the ruliad, within our sort of physical universe, we have black holes that are these things that are sort of lumps of that we don't get to see inside those. And for example, in physics, a black hole, well, at least the simplest kind of black hole, is one where essentially time has stopped, where if we're thinking about these rewrites happening to our hypergraph inside the black hole, there just isn't another rewrite to do. So time stops. And that's kind of what's happened inside that sort of sub-ruliad kind of thing. So in this hierarchy, we could imagine things at different levels in the hierarchy, but the only level of the hierarchy that we are, it's because we're here, we get to play in this level of the hierarchy, and that's our reality, so to speak. Well, okay, so the ruliad, this necessary thing that in a sense is there's no question about whether it exists. It must exist. It is just a matter of the definition of terms that the ruliad is what it is. Then the question is, it is much less obvious that we exist. The fact that we exist, there is a contingent fact needed that we are in the ruliad. Once you know that, then it is then the sort of the rest of existence follows from that. Well, so one of the things that then happens is to ask, well, what else is in the ruliad? What else, what other samplings of the ruliad are there? I mentioned the kind of the current computer science sampling of the ruliad of one thread at a time. Another sampling is mathematics. Mathematics is a different way. The mathematical observer is a different kind of observer of the ruliad. I mentioned that the physical observer is very time-oriented. The mathematical observer is much more kind of space-oriented. And in a sense, what's happening, so how is there even a correspondence between mathematics and something like the ruliad? Well, the answer is, and I just wrote a lot about this, that one can kind of view, let's ask the sort of the meta-modeling question of what really is underneath mathematics. What is mathematics made of? It's a question that people really asked quite a bit at the end of the 1800s, and that kind of led to mathematical logic and so on, this way of sort of the axiomatization, axiomatic specification of mathematics that led to things like combinators, that led in the end, in my own work, led to kind of the whole symbolic transformation rules construction of Wolfram language, which has been sort of that you know, the goal of Wolfram language is to provide this kind of computational language, which is sort of a computational notation for describing the world, but it's a notation for describing the world that is a bridge between the way the world actually is and what we humans care about. It's a language that we humans can understand, and it's constructed to be one that is sort of accessible to humans and applicable to the world, so to speak. So in any case, that sort of branch of sort of the imagination of what mathematics was made of is what in the end led to, for example, the structure of Wolfram language and so on, and the whole set of ideas around transformations of symbolic expressions and so on. But in the other thing that one can do is start saying, well, okay, what really is mathematics made of? Well, we can say, well, there are these sort of axioms and their theorems, and there's a whole way in which, you know, from one theorem, from let's say two theorems, you can prove a new theorem. You can take axioms and use them on a theorem to prove another theorem and so on. You get this giant network of all possible theorems. And in that network, for example, proofs of theorems become paths in that network that go from one proof to another, for example. And so this idea of this sort of network of all possible theorems, that's the story that is just like the story of the ruliad and just like the story of space. It's a story of this construction of sort of things based on rules constructed in all possible ways. And the question then is, we can ask sort of, what is the mathematics of all possible mathematicses? And right now, we're even in the way that we usually model mathematics, we're talking about axiom systems and, you know, P NAND Q equals whatever. We've already got things like variables and operators and so on. We can actually go below that. We can say, what's the sort of computational underpinnings of that? How do we build up to that from something even lower level? And what we realize is that what we start from are essentially atoms of existence. There's sort of an underlying structure, which is this collection of atoms of existence. Those are kind of the data structure of the ruliad, is atoms of existence. We've been calling them EMES, E-M-E-S. And in the case where we interpret the ruliad in terms of physics, those atoms of existence, those EMES, are interpreted as atoms of space. But those atoms of existence can be something different, this sort of sub-axiomatic layer of mathematics. It's kind of as if and we can see this explicitly if we use something like combinators as this kind of sub-axiomatic layer, we can see this combination of combinators. We can interpret that as meaning true and that as meaning and so on. We can build up from sort of the low-level machine code, we can build up to the axiomatic level of mathematics and then beyond. But so we kind of have this view of mathematics as this giant ocean of theorems proving theorems and so on that emerges from this kind of sub-axiomatic level. One of the things that then a question is, okay, what does the human mathematical observer observe in all of this? Because that very low level is, you know, the microscopic sort of updates of an automated theorem proving system, sort of proving pieces of mathematics. And in fact, as a human thinking about mathematics, you tend to think about things at the level of, oh, we've got things like the Pythagorean theorem. We've got sort of big notions that we can then work in terms of. So this is very much analogous to what happens in the physical universe and with space. We can think about things, we can say, well, underneath, there are these atoms of space and there's all this computational irreducibility, all this stuff going on, but we, operating in the universe as observers like us, can just think about things in terms of motion, in terms of continuum space, approximations to a continuum space, in terms of all these kinds of things. We have a high-level view of space. We're not dragged down to the level of atoms of space. Well, in mathematics, the same thing happens. Mathematicians have a high-level view of the structure that is kind of the ultimate metamathematical space. We could be down at the level of the axiomatic level or even the sub-axiomatic level, looking at these sort of microscopic details of how mathematics is put together. But in fact, when we do mathematics, we're talking about things like the Pythagorean theorem. Now, even if you go from the Pythagorean theorem down to the current sort of axiomatic level of things like set theory, the Pythagorean theorem might be on the order of, I think, 7,000, on the order of maybe in a typical sort of proof-assistant formalized mathematics system might be maybe made up from 7,000 sort of sub-theorems. And if you really unroll it all the way in terms of axioms, it's on the order of 10 to the 30th underlying axioms of set theory that you need to sort of build up the full Pythagorean theorem. So this thing that we think of as the Pythagorean theorem is pretty big relative to the underlying atoms of existence, well, even the underlying axiomatic level of mathematics, which is the axiomatic level of mathematics is kind of the assembly language of mathematics. The machine code of mathematics is something sub-axiomatic, even below that. But so the question then is, well, is it possible to do mathematics at the level of talking about the Pythagorean theorem? Or every time I talk about the Pythagorean theorem, well, I have to drop down to saying, oh, but by the way, I axiomatize it this way, and real numbers work like this, and we've got all of these chains of things that we have to talk about there. The big fact about mathematics is you don't need to do that. The big fact about mathematics is it's possible to do mathematics at a higher level where you talk about mathematical concepts and you're not dragged down to the level of essentially atoms of existence. And so what's interesting there is the fact that that's possible, the fact that higher level mathematics is possible is happening for sort of the same reason that a higher level description of space is possible. But it's a little bit different because what we're dealing with is that there are human mathematical observers observing the ruliad, the same stuff that they observe in physics, but observing it in this mathematical observer kind of way, but able to do that because they're sort of computationally bounded, et cetera, et cetera, et cetera. The things that they're observing are these computationally reducible slices that are the things that we think of as higher level mathematics. Now, as I mentioned, kind of the mathematical observer seems to more build up this kind of fabric, this entailment fabric of theorems entailing each other as this kind of fabric of which theorems can consistently be considered to be valid, so to speak. And so and that's something that you're sort of building up spatially. You're trying to extending your entailment fabric, and that's your kind of view of mathematics, is this stuff contained in the entailment fabric. So, for example, all kinds of funky things happen. Like, for example, let's say you introduce a false proposition into your entailment fabric. One thing that's been known since the Middle Ages is this idea, it's called the principle of explosion, that in sort of standard logic, once you introduce a false premise, you can prove everything from that false premise. It's the analog in metamathematical space of a white hole in physical space. It spews out everything. And so as soon as you introduce that kind of rulial virus, so to speak, into your, or metamathematical virus into your system, it's going to take over everything. It's going to prevent you from having a coherent entailment fabric that you can build up. And that's kind of how you have notions of truth and falsity in those kinds of settings. It's actually, the notion of falsity is very similar to the notion of destructive interference in physics, where what seems to be happening when you have those, the two-slit experiment, the photon can go through one of the two slits. And what's happening is those two photons are winding up, those two possible paths are winding up in different places in branchial space. And as an observer in branchial space, you have a bounded extent in branchial space. And so those, in order to reach out to both ways the photon could have gone, you have to be very, very extended in branchial space, which kind of fuzzes out everything else. But basically you can't maintain coherence as an observer in branchial space. And so that's sort of why you have to conclude, well, the photon actually didn't go that way. I didn't notice it went that way. Therefore, it's sort of destructive interference. So in any case, well, let's see, the things that I talked a little bit here about metamathematics. There's a very interesting thing, as far as I'm concerned, is empirical metamathematics. I started off looking at Euclid. I've looked at some other systems now where you can kind of look at the structure of theorems in metamathematical space. And what theorems, just like we talked about branchial space and this sort of how these different branches of history emerge, so similarly it's sort of how these theorems emerge, what's the common ancestry of theorems, how do the theorems lay out in metamathematical space. But you can do empirical metamathematics. You can ask, what is the structure of metamathematical space? What is the geography of metamathematical space? Where are the places that people have picked out to put settlements in mathematical space, to actually have named theorems, named theories of mathematics, and so on? And you start realizing that things like dualities between different kinds of mathematics are features of kind of motion in mathematical space, are features of kind of homogeneity of mathematical space, being able to transfer from this one place that's described this way in terms of algebra, let's say, to this other place described in some piece of number theory or geometry, whatever else. That's sort of a different place in rulial space, a different place in mathematical space. But the fact that there is sort of pure motion between these, the fact you can transfer from one to another, that's sort of the cause of these kind of dualities in mathematics. These things are a little bit captured by things like category theory. I think the thing that category theory tends to do is it's an attempt to have a theory which does not admit the full sort of computational irreducibility of what's going on. It's an attempt to carve out a piece, a sort of computationally reducible piece of what's happening. And the big thing in category theory is this idea, you have morphisms, F goes to G, goes to H, whatever. But you believe in sort of this compositionality idea that if F goes to G, goes to H, then there's also a morphism that goes directly from F to H. And in the world of computational irreducibility, that's simply not true. And it will not be the case that there's that the morphism that goes from F to H is sort of on the same level as the ones that go from F to G, G to H, because it has fundamentally more computational work to do than those lower level morphisms. But if you assume that isn't the case, if you assume that's not happening, if you kind of assume a certain degree of computational reducibility, then many other things follow. And that's sort of how category theory is providing a kind of higher level description of what's going on and a sort of a meta level description of some aspects of mathematics. In any case, the thing that I think is really fun is that empirical metamathematics is something where you get to do experiments and you get to ask questions about, well, what is the structure of mathematical space? And, we know these geographic waypoints in mathematical space. Those are a good place to start looking in terms of understanding space in general. And it's just like, if we're trying to understand the structure of space-time, well, we get to see some stars out there and we get to look at the characteristics of stars and the motion of stars. And that's kind of our sampling of how space-time works. And we have to infer from the motion of stars what the structure of space-time is. And so similarly, we have to infer from the sort of human settlements in mathematical space what the ultimate structure of mathematical space is. And so one of the things I'm sort of curious about is whether we will find evidence of features of our physics project first in empirical metamathematics before we find it in astrophysics, for example. And that would be kind of an interesting thing to be able to see sort of a different slice of the ruliad that we can sort of see empirically what's going on in a completely different way. So just to mention sort of another piece of this picture is in computation and computer science and so on. One of the things I've been interested in is to understand this notion of multi-computation and to really see to what extent one can turn that into a thing that we humans can think in terms of. It's not very natural for us humans. We tend to be, as I mentioned, we very much believe in our persistence in time. That's a very core feature of our view of ourselves, is that we are persistent in time. We have this thread of experience going through time. That's a very single sequential view of the world. It's not very immediately compatible with this multi-computational view of all these different threads and so on. But so the question is, can we do what I've tried to do for the last 40 years or so with Wolfram language, which is, can we, in Wolfram language, we're trying to capture in our language this bridge to what humans can think about, that part of the computational world that we humans care about and can think about, and a language for us to think about those things. And so I'm then interested in to what extent can we do the same kind of thing for multi-computation and have sort of a language, a human understandable way to think about multi-computation. Why would we care? Well, here's a big reason. You know, I think that multi-computation is kind of the fourth great modeling paradigm for science. You know, the way I view it is, you know, back in antiquity, people had this kind of very structural view of the way one would think about science. And the big question was, what are things made of? Are things made of atoms? Are things made of this? Are things made of that? Many fields of science are still in that structural phase. A lot of biomedical science, for example, is still in the what are things made of type phase. And that's the kind of reasoning that's going on there. Then sort of the big sort of jump forward for science in the 1600s was this idea of let's use mathematics to describe the natural world. And that has the feature that there's kind of among other things, there's a notion of time in there, but it's time as a parameter in equations. So it's really time as something that is just a knob you can turn, and you get these conclusions about what happens. And that's sort of the place where there's powerful science that's all about computational reusability. It's all about you can just turn the knob of time to wherever you want. Okay, then we get to the 1980s, when something I was deeply involved in is kind of this computational paradigm for thinking about science, where we just say, you're given the rules. You're not told there's going to be a solution to the equation or something. You're just told, here are the rules, you can run them. And that gives you this notion of time as this kind of linear thread, and this idea of computational irreducibility and so on. That's kind of the linear notion of time, but irreducible time. And that's kind of the thing, the kind of modeling paradigm that emerged, and that's given us all of the sort of computational modeling idea, this notion that really is a very, very transformative thing, I think, for science, this idea that one will model things in the world in terms of programs, rather than in terms of equations, rather than in terms of saying just what they're made of, but in terms of programs that are runnable, so to speak. And that's been a big idea in the last couple of decades that's emerged across sort of all possible areas of science. Well, the new idea is this multi-computational idea. Instead of single threads of computation, we're dealing with all of these branching, merging threads of computation. That means we no longer have this notion of time, that's this sort of linear notion of time that we have in the case of sort of the third paradigm of science. In this kind of fourth paradigm for science, the multi-computational paradigm, even this idea that there is a definite thread of time and we can just sample it at different moments, that's no longer there. There's this complicated mass of different sort of threads of time. And the only way we get to tell what's going on is to say, we are going to be an observer and we are going to sample this system in a particular way. And so the observer becomes very critical in this multi-computational view of things. But the thing that I'm interested in is to try and figure out, how do we get the sort of the description of this multi-computational way of looking at things to be such that we can reason in terms of it, we as humans can reason in terms of it. I should say that a big piece of what I'm also hoping we'll get to in the next little while is kind of a general observer theory. What can observers be like? What is an observer? What does an observer actually do? An observer basically takes, well, in the end, we human observers take everything that's going on in the world and eventually shovel it into our brains. And we do that through our senses. We sort of shovel it into, well, there's this image on our retina, there's this, sound that goes through our auditory nerve, whatever else. It's shoveled into our brain. And so all of these different things, we've got all these different complicated technologies and sensors and so on. They were all ultimately turning the things in the world, the 10 to the 30th atoms that some sensor is sensing. We're turning that into something that we can sort of see with our eyes and make a conclusion about. So in a sense, it's a big reduction of information that's going on in this process of observation. And I think the thing that to understand is that a lot of that is it's about kind of a lot of it is about things analogous to phase transitions, where there's a lot of detail about is it going to turn into is the magnet going to magnetize that direction or that direction? And there are lots of little pieces that go into it, but in the end, the answer is it magnetized up or it magnetized down. And it's that kind of thing that is sort of the process of being an observer. And I guess that what one thing to try to understand is sort of what is the big theory of being an observer, and how does that theory work when you have that observer endogenously within the ruliad? So that's sort of a coming attraction and something to really understand and to really catalog. It turns out there are 10,000 kinds of units, for example, of measure that we've sort of cataloged and curated for Wolfram Alpha and for Wolfram language. So we kind of know what those are, and there are all these different kinds of measuring devices. What's really the meta model of what's going on in all those systems? And that's something we need to know in order to really be able to have the right parameterization of that to build sort of a multi-computational language for describing things. But one of the things that I realized is that we've been looking at recently is take Wolfram language, which is sort of the richest way of describing computation, I think, that exists today. And Wolfram language is based on a very definite idea. And sort of 40 years after the fact, 40-something years after the fact, I'm kind of I realized that I dodged a whole giant flotilla of bullets, so to speak, in the way that it was constructed with things that I didn't really realize at the time. Because the fundamental idea of Wolfram language is everything is represented in terms of symbolic expressions, and the sole operation of the language is making transformations on symbolic expressions based on rules that have been specified. That's what the language does. That's what gives one all of the things that are in Mathematica, Wolfram Alpha, all these kinds of things. That's ultimately what's going on. It's just transforming symbolic expressions according to rules. Ironically enough, that's a very similar idea to the idea that underlies our physics project, although I certainly didn't see that until all the threads had already come together, so to speak. But one of the features of the way Wolfram language works is these transformation rules, they just keep on getting applied until the symbolic expression they're operating on no longer changes. And you say, I've got my input, it's kind of this symbolic expression to which lots of rules can be applied, lots of things happen, and then in the end, out pops the answer, the expression that doesn't change anymore, the fixed point, that's the answer. So it's this, and in the process of getting to that answer, there might be many different ways you could apply those rules. We just pick the first one that works. And we're going through this one path, through this kind of multi-way system of possible rule applications. We go through this one path and get to the answer, and that's what we present to the user. In multi-computation, that's not really what's going to go on, because there isn't one answer. There isn't a fixed point, typically. There's this whole sort of branchial space of possibilities happening at any given time, that we have to somehow represent all of that. But the thing to understand is this. Just like in physics, we say there's things like time-like process separations, things follow each other in time, space-like separation, things are happening at the same time in different places in space. In our models, there's also the notion of branchial separation, things that happened on different branches of history. There's also rulial separation, things that happen in different branches of history corresponding to the application of different rules. So we've got these different kinds of separation between things. And what I've been thinking about recently is how that relates to kind of the way to sort of make languageify multi-computation. Time-like processes are very much sort of the traditional view of programming, in a sense that it's this procedure of you do this, then you do this, then you do this. You take a thing, you do this to it, then you do this to it, then you do this to it. There's this kind of set of causal dependencies that goes sort of down with time. There's the thing, then there's the new version of the thing, new version of the thing, each depends on the other. Then there's kind of space-like computation, more like array computation operations on lists, things like that. You've got this whole big list of data, you do something to each element of the list. Those are things kind of happening in some sort of space-like way. And so you can start thinking about functions like the nest function in Wolfram language is a time-like operation. Nest lists, well, listability is a space-like operation. Nest list is a combination of space and time operations, and so on. Okay, well then, what about branchial separation? What about branch-like computations? Well, that's like you have two choices. You might apply a rule in two different ways. You might have a conditional, which can go on two different branches. Those are different choices. And you can imagine then making, for a particular computation, making its multi-way graph, where there are branch-like separated pieces of that multi-way graph. So those are what in distributed computing one might call things like race conditions and so on, where it's like, did this happen first or did that happen first? We don't know. They're both sort of possibilities. That's described now in terms of this multi-way graph, in terms of separation in branchial space. And so this is kind of a way of thinking about kind of the organization of distributed computing and so on in terms of possibilities in branchial space. And what you realize is that just like there are reference frames in space-time, there are reference frames in branch time and so on, there are these different ways to think about what's going on in the computation, these different kinds of different slices that one can take depending on sort of which parts of where in branchial space one is living. Well, there are a lot of ideas around this, and sort of the challenge is to make a thing that can actually connect to humans, because it could be that it's just, sorry, but we just don't do it. We humans just don't get multi-computation, maybe. But let me make another comment. The story, in a sense, of progress in technology and science is a story of gradual expansion in rulial space. It used to be the case that we had a certain description of the world that was in terms of certain kinds of concepts and so on. That is a particular place in rulial space. And with other concepts, you couldn't get there with that description. Similarly, our sensors, before people had invented electronic amplifiers, for example, very small effects were not detectable. We couldn't measure them, we couldn't observe them, we couldn't convert them to something which is accessible to human senses. So in a sense, the sort of story of the expansion of technology, the expansion of ideas, paradigms, science, and so on, is this gradual expansion in rulial space, where we get to have a larger domain in rulial space, where we can where that's part of our understanding of what's going on. So in a sense, what we're asking for now is to expand our domain in rulial space to be able to deal with the multi-computational paradigm. Now, one of the things that's perhaps ironic and worth realizing is that, in a sense, our existence, the fact that we have a coherent existence, is a consequence of the fact that we're quite localized in rulial space. And one could imagine at some time in the distant future, when it's all, uploaded souls in some, ultimate virtual world type thing, you could say, well, let's just expand in rulial space. Let's explore more and more of the ruliad. Maybe the future of existence is the exploration of more and more of the ruliad. And we realize, well, gradually we'll expand our domain in rulial space. We'll have minds that are more broadly spread in rulial space. But the downer of that situation is, once we expand all the way to the full ruliad in rulial space, we no longer have a coherent existence. In a sense, by extending our domain in rulial space too big, we're no longer coherent. There's no longer an us to talk about, so to speak. So it's kind of an ultimate, ultimately it's, be careful what you wish for, but certainly the expansion from where we are now to encompass this multi-computational paradigm and to have kind of a language to describe that is something that I think we're going to be able to do. I think it's likely we're going to be able to do. Every time you expand in rulial space, every time you pull in a new paradigm, it's a difficult thing for people to do, but it's something that, it's an interesting thing to try to do. Now, with this multi-computational paradigm, there's a lot that can be done in looking at all sorts of areas whether it's understanding biological evolution and understanding the fact that, when you have a genealogical tree, the distance on the genealogical tree is branchial distance, the distance between, in physical space is physical distance. We've got the same kinds of stories in sort of understanding the meta model of biological evolution that we do to some extent with physics. I don't know whether speciation corresponds to event horizons, something like that. That's still to be figured out. But there are a lot of different areas. Another area I've been very interested in is molecular computing. And particularly in molecular computing, it could be that the model that we have of given input, crunch, 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 given output is not really the right model. That really the right model is something more about all these different threads of possible reactions with all these different molecules that are doing them. And it could be that the idea of chemistry, where we just say, and what we care about is the concentration of different kinds of molecules, isn't enough of the story, and that there's more that kind of goes in a sub-chemistry level, so to speak, where we're looking at the sort of individual causal relationships between atoms or between molecules. This molecule interacted with that molecule, A interacted with B, they went off and did other things, and then those specific molecules, A and B, met again and did something else. The causal relationships there, which are not captured in traditional chemistry, which is just concerned with overall concentrations of molecules, might be important. In particular, they might be very important in molecular biology. And one of the things I've been increasingly realizing is that sort of in the what is life question, I've been increasingly realizing that, one thinks about material objects, solids, liquids, gases, things like that. These are kind of homogeneous thermodynamic kinds of concepts. But what's happening in life, it's like a machine. It's kind of the machine phase of matter, where all those little all those little cytoskeletal elements and so on, all those enzymes, all those sort of chains of molecules and so on, they're all carefully orchestrating what happens in a living system in a way that's very different from the way that things tend to happen in your average solid liquid gas. I think that the thing that's sort of an interesting analogy perhaps is that if we look at an electron gas, for example, we could have in some semiconductor, let's say, we could have a bunch of electrons hanging out in a semiconductor, just doing things like a gas of electrons. Or we could have a microprocessor where there are specific channels that have been set down and etched out of the silicon to guide that electron gas in a very specific way. And the thermodynamics of a microprocessor is not the thermodynamics of the generic electron gas. It's a very different thermodynamics. It's something where we don't think we have kind of a global theory of it at this point. It's just the particulars of a microprocessor. Well, I think it's the same kind of thing with life, that there is, you can say a little bit from at a generic level, but at some level, it depends on all the details of all those little fibers and all those little sort of chains of molecules and so on, specific molecules, not just concentrations of molecules, but specific. This molecule was embedded in this membrane and opened this pore, which lets this specific molecule through. We don't tend to think at that level because there's an awful lot of molecules in us. And we say, oh my gosh, we can't think at that level. We have to think at some more aggregated level. But I think it may very well be that the molecular biology observer cares about some of those molecular details. If it was the case that for doing physics, we had to understand things at the level of atoms of space, for doing mathematics, we had to understand things at a sub-axiomatic level, we wouldn't be able to do those higher level things. In molecular biology, for example, we imagine that there is a higher level theory. We're not quite sure what all aspects of it are. And there may be sort of big pieces of sort of the organization of molecular biology, just like we're in genetics, kind of the realization that digital information was being stored in DNA was sort of the crucial organizing principle that led to modern genetics and so on. So also there may be a sort of crucial organizing principle that's something more about multi-computation that allows one to understand sort of molecular biology at a larger scale. But this is a question for lots of different fields. For economics also, what is the correct meta model for an economic system? Is it this network of transactions? What is the economic observer like? It could be that, yes, there is a predictable economics about some weird quantity that's one where we say, well, that's nice. And yes, you can predict that. But unfortunately, that isn't what we as humans observing economic systems care about. It's something where sort of there is an understandable thing, but it's just not at the level that it's not a slice of things that happens to be what we humans care about. But in any case, the things that we're sort of trying to pursue are sort of understanding this multi-computational paradigm, applying it, and seeing, sort of trying to nail down that paradigm, clean up the paradigm, languageify the paradigm, so to speak, and then to see how that paradigm described in those ways can be applied in all these different fields. And I think it looks to be an extremely productive set of things that are possible there. And well, in any case, those are some of the things that that are sort of in motion right now. And I'm probably forgetting some huge projects that we're planning to do. I will say that one of the things that's happened is there's sort of both the problem of what is the science and the intellectual content of what has to be done, and how should this be done? How should it be organized in the world with people and all those kinds of things? And so one of the big things we're doing is launching our Wolfram Institute, which I'm happy to say is off to a really good start. And it will be officially launching in another, what is it, month and a half or so. That's something where the goal is to really take what we've learned from the 35 years I've been running our company, for example, about sort of how to organize energetic research and development projects, and how to kind of have a managed research type of mechanism, taking that and applying it to basic research to move forward some of the things I've been talking about in an effective way. That's kind of the mission, the objective, the tactics of our institute, and it's something we're both in terms of funding and people working at the institute. That's something we're sort of actively developing right now, and it's going. I would say it's going very well, which is really nice. And you know, we're going to be able to do a lot of great science there, and it's going to be something that sort of a complement to what we do at the company, where we're building essentially tooling and technology, which happens to have enabled this kind of new level of science. Now it's a question of, well, can we take that new level of science and really give it the right environment where it has the possibility of sort of flourishing as much as it can, and that's what we're trying to do with the Institute. You know, it's an interesting thing. I realize I have a big box here. This is a big box this is a boxed set of collection of books that represent some part of the last 30 years of my life. And this is sort of a 20th anniversary set that's coming out in a few weeks, I think, of celebrating the 20th anniversary of my book, A New Kind of Science. There's a little book there that is about 20 years of a new kind of science. And it's interesting to reflect on kind of why it needed to be the case that these different steps that I, for example, happen to have gone through in doing science and doing technology all seem to have been necessary ingredients to get to where we are today. I mean, I started off doing particle physics and things when I was a kid, and then ended up doing sort of building my first big computer system in the beginning of the 1980s. And sort of that, knowing particle physics and theoretical physics in general, sort of doing this step of kind of creating a computational system from scratch, my first language from scratch, and understanding those things and seeing how that worked, then coming back and working on simple computational systems in the 1980s. And at that time, very much in the service of understanding sort of complexity in the world, but then realizing that there was something much deeper that came out of just this pure computational paradigm, then going back into working on Wolfram language and so on, and then New Kind of Science, and then from that to eventually to our physics project. But it's been interesting to see that these sort of succession of layers of doing science, then technology and science and so on, have been sort of a necessary tower that had to be built. And I'm continually amazed that we actually managed to do a bunch of this stuff, because it's, you know, it was very dicey in a sense, because it's kind of like you have to have a certain sequence of things align to make it possible to do these things. But I think the thing that's really amazing right now is that there's an awful lot of stuff that's aligned, and we're in a position to do some really exciting things. And anyway, I'm having a great time doing this stuff. I just loop back to the project I'm doing right now, which is looking at the second law of thermodynamics. I can date rather precisely when I really got first interested in that, which is June of 1972. And it was kind of based on this picture on the cover of a book. Oh, I don't have the book here right now. That shows, gas molecules in one side of a box, and they gradually spread to other parts of a box. And one of my first computer simulation programs was an attempt to reproduce that simulation. And I finally now know how to do it. And finally kind of think I really understand what are the things that go into the second law of thermodynamics. And it becomes a story, just like these other things, of the interplay between our computational boundedness as observers and the computational irreducibility of underlying dynamics. And one realizes that the second law of thermodynamics is true up to a point. It's not as true as people have thought it is. It's true up to certain assumptions you make about observers, up to certain features of the underlying system. And it is not one of these things that is sort of tautologically true, as people have sometimes assumed. It's something that is a fact that emerges from certain assumptions about the world.